We're now moving on to 11.3, solubility. In this section, we're going to describe the effects of temperature and pressure on solubility, state Henry's law and use it in calculations involving the solubility of a gas in a liquid, and explain the degrees of solubility possible for liquid-liquid solutions. So let's first start talking about what solubility is. And if you've ever tried to make something like sweet tea like they do in the South, or if you've ever tried it, the process of making it, you don't just make iced tea and pour sugar in while it's cold. You are mixing in the sugar while the tea is steeping, while it's nice and hot, because sugar is easier to dissolve in hot water. Okay, and that means that even these highly soluble or highly water-soluble compounds have a limit to how much can actually dissolve in solution. So solubility is the maximum concentration of a solute that can be achieved in a particular solvent under given conditions when the dissolution process is at equilibrium. Your book in this chapter doesn't really talk too terribly much about the units of solubility, but it's generally given in grams of solute per 100 grams of solvent. So the higher the solubility, the easier it is to dissolve something in water or whatever your solvent is. Now, if the concentration of solute equals its solubility, then we say that the solution is saturated. Okay, so that means the complete maximum amount of solution or amount of solute is dissolved in solution. If we are of a solute concentration less than the solubility, this is an unsaturated solution. So this is generally what you'll have like when you have iced tea that's been sweetened with sugar. It's generally unsaturated. If you have something like sweet tea, after it cools down, you may notice at the bottom of the tea there's some pieces of solid sugar, and that's because now your solution is saturated. So we'll talk about how solubility varies with temperature, but you probably can already tell that for solids, solubility goes up as temperature goes up in general. You can make what is called a supersaturated solution, and this occurs when the solute's concentration is actually greater than the solubility that it's supposed to have in solution. This is an example of a non-equilibrium state. That's pretty much all we're going to talk about, but these are very unstable solutions. You give them a little bit of a flick, or you put in like one tiny extra crystal called a seed particle or a seed crystal, and the whole excess is going to crystallize out of solution. I know quite a bit about supersaturation, as that was a major part of the research I did talking about supersaturation of water in the air and humidity. So there's a few different factors that influence how much of a solute can dissolve in a solvent. The first one being the nature of the solvent and the solute and the interactions between them. Are we talking about, gas in a liquid, solid in a liquid, liquid? The temperature also is a big factor. And when we're dealing with a gaseous state, the pressure is also important. And I don't know if my microphone is picking up those big thuds, but I apologize. My cat's trying to get into things right now. Okay, so let's start by talking about gases dissolved in liquids. So the first thing to think about is when it comes to gases, we don't have solute-solute intermolecular forces. Because remember, gases, specifically ideal gases, don't have interactions with each other. So the only intermolecular force that's going to affect our solubility is the solute-solvent interactions. So the more they're able to interact, the more soluble the gas is going to be. Now, temperature affects the solubility of a gas. For gases, though, we touched on solids, but for gases, the higher the temperature, the lower the solubility. And this is because you increase the temperature, you're increasing the kinetic energy of a gas, so it's moving faster. And so then it's able to get to the surface and leave the solution. So here's a graph showing the solubilities of different gases in water. And you can see as the temperature goes up, their solubility decreases. This is really important for things like climate change. When temperature goes up, and we're raising the temperature of the oceans, like I said last section, the solubility of things like the oxygen in the water, which the fish filter in through their gills, decreases, meaning the oxygen leaves the water and there's not enough then for the fish. This can also be a natural thing that occurs, and I'll talk about that in a moment. Pressure also has a big effect on the solubility of a gas and a liquid. The gas solubility, we're calling it Cg, and its partial pressure, Pg, are directly proportional, where the proportionality constant is K, and it's the constant of the particular gas-liquid system and temperature that we're looking at. And this is called Henry's law, and we can use this to predict the solubility of a gas. So A and B have a couple examples. In A, those are some small bubbles of air and some chilled water. So the water then is warming up to room temperature, and those gases that were dissolved in the water are coming out of solution. And then in B, these large-scale fish kills happen in natural waters. Thermal pollution can do this when it warms up water too much. It can also happen with natural processes too, like for instance, just with the weather cycles as it starts to warm up for some lakes. The oxygen level decreases and the fish die. For instance, when I used to do water quality monitoring for Canyon Lake and Lake Elsinore, down in the Murrieta area, Lake Elsinore, at Canyon Lake, which is a private community, it's kind of like Spring Valley Lake. They had a fish kill almost every year when the lake would, as we call it, turn over due to the temperature changes. Though there was one year it was really bad, and I think, and it was while we were still sampling. It wasn't a day that I was doing field work; someone else in the lab was. But if I recall, they said it was almost like a meter deep of dead fish. So that's fun. Another example of gases in liquids is soda. So, fun fact, it's actually, when you have a closed container of your soda, it's actually a super saturated solution of carbon dioxide dissolved in mostly water. And when you're opening it, it makes that sound, right? What's happening is you're reducing the pressure above the gas. So we'll talk about pressure. We kind of started talking about pressure, but basically, as you increase pressure, you're increasing solubility because you're pushing down on that gas. You're pushing more and more gas into solution. So when you go and you open that can of soda, you're lowering the pressure now because now there's less pushing down on the gas or on the surface of your liquid, and now it's able to come out of solution. So this is why all that excess carbon dioxide leaves. If you go and you're being, kind of a butthead to your friend and you shake the can before you give it to them and a bunch of carbon dioxide comes out, when you're shaking it, you're adding kinetic energy. You're slightly warming up the temperature. You're agitating it, so those bubbles are able to come out more because you've increased the temperature a slight amount. So another interesting thing with this is when a soda goes flat, you've actually hit equilibrium of dissolved carbon dioxide in the soda versus in the gaseous phase. So technically, there's still carbon dioxide. They're still bubbly, but, it's actually dissolved now. So let's go ahead and look at an example using Henry's law. We're told at 20 degrees Celsius, the concentration of dissolved oxygen in water exposed to gaseous oxygen at a partial pressure of 101.3 kilopascals is 1.38 times 10 to the negative third moles per liter. Use Henry's law to determine the solubility of oxygen when its partial pressure is 20.7 kilopascals, the approximate pressure of oxygen in Earth's atmosphere. So let's first just kind of write down Henry's law, and that's that Cg is equal to Kpg. So we were first given a pressure and a concentration, but we don't know K, so we can use those initial numbers to figure out K, because the K is a constant. So then K is equal to Cg divided by Pg. And we were told that our concentration is 1.38 times 10 to the negative third moles per liter. That's why it says mole and then liter inverse. That just means moles over liter. Okay, divided by the pressure, 101.3 kilopascals. As long as we are being consistent with our units, this is fine. We don't have to change them to regular pascals. So this gives us a K value of 1.36 times 10 to the negative fifth. And with some kind of interesting units here, we have moles per liter per kilopascal. So now we know K, and we know our pressure for the system, the new system we're looking at. So now we can find the solubility of oxygen. So we need Cg. Okay, it's equal to K times Pg. Since we have K now, we have 1.36 times 10 to the negative fifth mole inverse liter inverse kilopascals times our pressure, 20.7 kilopascals. So we can see those cancel, and we're left with moles per liter. So our Cg then is equal to 2.82 times 10 to the negative fourth moles per liter. And moles per liter is molarity, so you could also just write it as big M molar. So just again, any units, as long as the dimensional analysis, so when you're looking at the units and how they combine, as long as everything works out, the units aren't that important, just as long as they cancel out properly. Okay, so let's look at another example here. I'm going to add a little bit here that I forgot to copy and paste. Okay, so we're told a certain species of freshwater trout requires a dissolved oxygen concentration of 7.5 milligrams per liter. We want to know if these fish could thrive in a thermally polluted mountain stream where the water temperature is 30 degrees Celsius and the partial pressure of atmospheric oxygen is 0.17 atm. And one thing that I forgot to copy and paste is that we need to see figure 11.8. And 11.8, if we go back, is giving us the solubility of gases at different temperatures. So we need to go ahead and find the oxygen, which is in red here. And at 30 degrees, I have a solubility about right there. And so we're going to go ahead and say that's about 1.15. So we're going to go ahead and say that the solubility concentration based off of table or figure 11.8 is 1.15 times 10 to the negative third moles per liter. So then that's where we get this 1.15 times 10 to the negative third moles per liter divided by the pressure that data is from, and that's also, when we look at that again, we're told at 101.3 kilopascal or at 1 atm. And we're going to go ahead and use 1 atm because that's what the second units are here. Okay. And so this gives us a K value of 1.15 times 10 to the negative third moles per liter per atm. So now we can go ahead and solve for the solubility at this lower pressure and higher temperature. So that's Cg is equal to 1.15 times 10 to the negative third times our pressure, and we're told this is 0.17 atm, so we see atms cancel, and this comes out to be 6.2 milligrams per liter, and this is less than the required 7.5 milligrams per liter, so no, the fish would not be able to survive. They would not thrive. Another place where Henry's Law comes into play is diving. So you can have what's called decompression sickness or the bends. And what happens is if you're scuba diving, um, you're inhaling air at these different depths, but the pressure of the atmosphere of around the divers is increasing due to the water above them. So it goes up 1 atmosphere roughly for every 10 meters of depth. So you start off at 1 atmosphere of pressure, and then you go down past 10 meters, and now you've added another atmosphere. So now you're at 2 atmospheres of pressure. So now what's happening is the air that's being inhaled, the gases are being inhaled at that higher pressure. So their concentrations of the gases dissolved in the diver's blood is proportional to that. So it's going up also because of the higher pressure, and higher pressure increases concentration and solubility. So when a diver now is coming back up to the surface, they need to do it very, very slowly, because what's happening now is that pressure around them is decreasing, so those dissolved gases now are less soluble. So if they go up too fast, the gases can leave the blood too fast and make bubbles that can make a bunch of symptoms from rashes and joint pain to paralysis and death. So to avoid decompression sickness, they need to go up at relatively slow speed, so about 10 or 20 meters per minute. So go up a little bit and wait for a minute, or go very, very slowly. Or take decompression stops, so again, pausing at several minutes at given depths. If this isn't successful, a lot of times the divers that have decompression sickness can be put with hyperbaric oxygen therapy and pressurized vessels called decompression chambers. So you've got some Navy divers that are undergoing training in a recompression chamber. And then B, those are some divers getting hyperbaric oxygen therapy. So for those of you that dive, this is why it's so important to avoid the bends. And we can have deviations to Henry's Law. And this is going to occur between a gas solute and solvent, of course, when a chemical reaction happens. And then also gases can form supersaturated solutions. I kind of already talked about that with carbon dioxide. But one example is ammonia, NH3. This is a gas at room temperature, but when you put it in water, it goes through an acid-base reaction with ammonia being a base and taking a hydrogen from water. And so then it forms NH4 plus and OH minus. So this doesn't follow Henry's law. With supersaturated gases, this is believed to have be the cause of a disaster in 1986 that killed more than 1,700 people near Lake Nyos in Cameroon. So they believe what happened was that there was all this carbon dioxide gas, which is generally harmless, but in this case, so much of it came out. So it was being compressed in and dissolved, and then it ended up being released. It's colorless and it's denser than air, so then it ended up replacing the air around people, so they had no oxygen and ended up suffocating to death, killing a bunch of people and animals. And so they've actually now added a vent so that the gas is able to leave in a very slow and controlled fashion, so that, a little bit of carbon dioxide is harmless. And I'm talking about carbon dioxide, not monoxide, which we already know is something that can kill people. But carbon dioxide can also be dangerous. Only something like this, not like, yeah, okay. So we can have solutions made of liquids dissolved in liquids. So both your solvent and your solute are liquids. If you have two liquids that are able to mix with each other in any and all proportions, we call them miscible, okay, meaning they can mix. So they generally have similar polarities, so like dissolves like, so generally like a polar with another polar liquid. And we say they have basically infinite solubility. I can keep mixing ethanol and water to my heart's content. They're really not going to stop being soluble in each other. Okay, ethanol is the alcohol that people drink to get drunk. Ethanol and methanol are very different. Do not drink methanol. That will kill you. Another example would be gasoline and oil. Those tend to mix very well. They're both nonpolar. Water and antifreeze are also very miscible. Antifreeze is quite polar. If you have two liquids that do not mix very much or at all, we say they are immiscible. So if you try to put, water and oil together, you don't see one solid layer. You see two separate layers. We say they have very low, but actually technically a non-zero solubility. So if I try to put something like nonpolar, like oil and water, I would end up with two distinct layers, and where I could actually see where they separate. So here's an actual picture of water and oil not mixing right here. So this is like vinaigrette dressings are usually made of water and oil, and you have to really shake them up and get them on your salad before they separate, and they still generally do, even on your lettuce, but it still tastes delicious. You can have liquids that have some mutual solubility, a moderate amount, and we call these partially miscible. So they might at first form one layer when you mix them together. It's like, okay, one layer, they're miscible, but as you add more, they end up separating. One example is bromine and water. On the left is bromine in this picture. Water is in the center. And when you mix them, what you notice is you see two layers, you see two distinct layers, but the water layer actually has color to it. And that's because there actually is a tiny bit of bromine, a small amount that's able to dissolve or be miscible with the water. So this is a saturated solution of bromine and water on top, and the bottom is a saturated solution of water in bromine. Now, when it comes to solids dissolved in liquids, in general, as we increase the temperature, we increase the solubility of the solid solute in a liquid solvent. And we can use this solubility to make a supersaturated solution. So here's a graph here showing how the solubility of several solids change with temperature. At the bottom, you have cerium sulfate, not really one we work with, but it actually goes against the solubility rules. It goes down in solubility with temperature, but it's already pretty low in solubility. But you can see here those units I talked about earlier in the chapter, that the solubility units tend to be grams of solute per 100 grams of solvent, in this case, water. So both ionic and covalent solids can dissolve in liquids. For instance, you have sodium, I think that's acetate, dissolving, making sodium plus and acetate minus. When you dissolve a solid in liquid, it's generally an endothermic process, so energy has to go in, and the system might get a little cold. If you add some heat, you're going to favor the formation of products. So you're going to make it so that you dissolve things faster and easier. So again, the solubility of most solids tends to go up as we increase temperature. To make a supersaturated solution with a solid solute, you would start by making a saturated solution of the compound at a high temperature and very, very, very slowly cool it to a lower temperature. If it's slow and careful cooling, the solid will not precipitate. And then at this lower temperature, you have a solute concentration greater than the compound solubility. Let's see if I can get this video to work, showing some precipitation from a supersaturated solution. So we have a supersaturated solution here, and if we add just a tiny little single crystal into it, which they're just doing right now, they're putting, it's called, you can say you're seeding it. You can see that crystallization starting right away. All that excess solute is now precipitating out. I like the way they did it. They made it really pretty. Sometimes you can just give them a shake or like tap the side and it'll work. But this is one of the more pretty ways to make a supersaturated solution and then precipitate out the excess. Hand warmers. So there was a period a few years ago where at grocery stores they'd make an announcement, if you want to get a free chamois or free gift, come to the back of the store. And you would go to this presentation, and they had these cool hand warmers where all you have to do is make it so this little metal thing just makes a little snappy sound, and then all of a sudden it forms this hard crystal and this hard stuff inside that's nice and hot and makes this great heating pack. And then it's reusable. All you do is throw it in some boiling water, and it goes back to being clear, and you're good to go. So this is a super saturated solution. So basically, when you're clicking that metal disc, you're doing a shock wave. So then you're making a couple molecules that are, above that saturation point. They hit each other, and they're like, oh, I want to form a crystal. I want to come out of solution. And then they start to form that solid, and more do. I have quite a few of these around my house. They work so very well. My problem is I always forget to boil them to redissolve the solid.